Hardy-Weinberg equilibrium. Okay, so if you were a population scientist and you were out studying a population, you would become very familiar with Hardy-Weinberg equilibrium, the formula to calculate that. It is a way of using numbers and counting individuals that will tell you what genotype is in the population, whether it's a homozygous dominant, heterozygous, or a homozygous recessive. And what they do is they look at that number, and if it does not match, so let's say they go in and they count. If the number they get does not match with what they're actually counting, that population is evolving, okay? But on the other side, if it does match, then we know that is a non-evolving population. Now keep that in mind. And so some of the things that they will look at as scientists to help determine this are the gene frequencies and the allele frequencies. You know, if you go back and remember a capital T, let's say that's a dominant gene for tall. And for so if you're looking at, say, like the gene frequencies, how much of that is in the population compared to how much of the recessive short, if the lowercase t equals short. And then all the allele frequencies both together here. Okay. Now, again, it gives a baseline of what a population that's not evolving should look like compared to one that is evolving. So remember, if it doesn't match, it's evolving. So if it does, then it's a non-evolving population. And so what does a population in equilibrium, or one that's not evolving, look like? Well, here are 5 things. You got to see it in your POGL. 5 conditions must be met, and it's very hard to meet these 5, but the population is large. That means no genetic drift. There's not going to be any migration. So remember, there's not going to be any new genes coming in and out. There's not going to be migration in or out. So that's going to not have gene flow. That's going to restrict it. That could cause equilibrium. No mutations. Well, you remember, you know, evolution is random. And so if you don't have mutations, you don't have evolution. So if you don't have mutations, there's no gene modification, and you're closer to being in equilibrium. Random mating. You know, around here, the deer, the male deer to bucks, they go through a sexual selection process where they fight each other for the right to mate with whatever females. And so if you just take that out and there's random mating, that's going to get you closer to Hardy-Weinberg equilibrium and no natural selection. Okay, if there's no natural selection, then the same thing, you're getting closer to Hardy-Weinberg. Now, let's look at this. This is the formula. And so if you know what the variables mean, you got it. Okay? And so I have them written down here, but I'll put it up a little more. This p squared is a variable for the homozygous genotype. Well, if we continue to use the t's for like tall, so that would be the homozygous dominant genotype. Then you're going to add that to the 2pq. Well, the 2pq is your heterozygous genotype. And then you can guess at what the q squared is. That's going to be your recessive, homozygous recessive genotype. And so you know you've got that. That's pretty straightforward. And I'm going to tell you right up front, most problems that you will get will either give you that one most of the time, probably 90% of the time. Sometimes they might give you that one, but either way, when you get that, it's not a problem, you've got it. And I'll show you, we go through an example. So get this erased. Move it up so you can get that on there. Q squared is your homozygous. And remember, this is going to be your homozygous dominant, your heterozygous, and your homozygous recessive. Okay. Now, the flip side of that coin. The flip side of that coin. Get this out of the way. You're going to have P plus Q. P plus Q. So these are the alleles of a trait in a population. So up here we were talking populations. Here now we're looking at the individual alleles. And so it's either going to be the P is going to be the frequency of the dominant allele in the population, so that capital T, that dominant T, and the Q is going to be that recessive trait there in the lowercase t. And again, we're setting you up pretty easy. And so I'll let you get it. Remember, P is always going to be the dominant trait, and Q is going to be the recessive trait. Now, you notice that up here it says equal to 1. And here it says equal to 1. This is the way you check to make sure you're doing it right. Once you get your P plus Q, if it matches 1, you got it. You're good to go. Okay? Now, I'm going to write this down here. And so make sure you're writing this down. So we're going to go, let's go over it again. There's P squared plus 2PQ plus Q squared. That's always equal 1. Remember, that's an important check. And then down here on the flip side of that coin, you got P plus Q equals 1. Again, there's that check, that number 1. Now, I want you to remember, you're going to solve this in a counterclockwise motion. Solve it in a counterclockwise motion. This is how I taught myself how to do this. And most problems that you read will give you Q squared. Once they give you Q squared, you just got to do one simple thing on your calculator and you'll figure out the Q. So what you're going to do is they give you a number, and then what you're going to do is you're going to square root whatever Q squared is. Once you do that, that's going to give you Q. Once you get Q, it's over. Now, they can give you this side, and then all you'd have to do is switch that up and work it backward that way. But we won't worry about that quite now. You can do that. It works. So once you figure out Q, so let's say Q equals 0.3. Well, you know, whatever we add to this, P's got to equal something when you add them up equals to 1. In this case, it's going to be 0.7. And so we know that we've got P. Now remember, we're following it. We're going around clockwise motion. And now instead of Q, you're squaring it here, what you're going to, or square rooting it, what you're going to do is take your P, whatever that number is, and then you're going to square it. And once you do, it's going to give you the P squared. And you already have the Q squared from the problem. Once you figure this out, remember, this plus this has to equal 1. So they probably won't give you this one, but you'll have to do the addition. Once you find this, go through, find this, add it up. Remember, it's got to equal 1. 1 is important. It's got to equal 1. And you write whatever that answer is up there, and you're done. It's over with. But remember, most problems will give you, once you solve for Q, you've got it. It's easy. The hardest part is knowing when you got to square root or square it. And again, you can reverse this. It'll reverse. But most of the time, they will give you this. Okay? Now, let's take this out. And let's look at a problem. So here we have frogs. And you can see there's dark green color, and then there's a yellow. Now, the dark green is going to be a dominant trait. And so here's that, the arrangement here of the alleles. And down here you've got, this is your homozygous dominant, your heterozygous, your homozygous recessive. And so you're going to be looking, they most always will give you, remember, they're always almost going to give you this number, whatever that percent of the population is. So if you look, they're telling us that Frog Island has 500 frogs. 500 total frogs. They came in, they did a count. And what they did was they found that 125 of them are carrying this homozygous recessive genotype. Well, so what we got to do is we got to figure out for Q squared. So what you're going to do is take 125, divide it by 500, because that's the total number of frogs, and it's going to give you 0.25. It's going to give you 0.25. And then if we plug it in, see, we know that Q squared is 0.25. Now remember, we're going clockwise. And so Q squared is 0.25. We have it. So what we do then with the 0.25, we do the square root, and then that gives us a 0.5. So now we know Q is 0.5. Now remember the rule. What do you got to add to 0.5 to equal 1? Well, 0.5. So now you got P plus Q. You know these alleles are distributed pretty evenly among the population. So if we keep following it, we finish that, we got that. Once we have this, and we do, it's over. You've got it. It's tapping out. You figure it out. P plus Q equals 1. Remember, gotta check. It's got to equal 1. 5.5 plus 0.5 does equal 1. Now what you do is you keep following it. You take the 0.5 and you square it. And when you square it, you get 0.25. You see what it's just like that on either side. Now, easy. You know you got this number now, you got this number now, and you know they both add up to 0.5. But remember, the magic number is 1. Magic number is 1. And so if you add 0.25 to 0.25, you get 0.5. And so that means this 2PQ, the heterozygous population, it's going to be over half of the population are going to be in that. So G, little g, capital G, little g. And so over half the population is going to be here, a quarter of the population here, and then a quarter of the population here.